Well, hello, everybody. This is efficient trading of aggregate bidirectional EV flexibility with reinforcement learning. I am Javier. I recently graduated from my master's in University of Alberta, and this is a project I did as part of my thesis. So to get started, I can just click it. Now it works. Thank you. Okay, sorry about that. To get started, we all know that the power grid is evolving. I'm just going to point out some of the key features here. We have distributed generation. Consumers are now also producers. This is in this rooftop mounted solar. We also have electrification. More things are becoming electric, and the things that are require more electricity. We also have renewables, which are non-dispatchable and intermittent. This means they are difficult to control and difficult to forecast. This all gives rise to the need for storage in the grid. In this project, we proposed using the batteries in electric vehicles that are connected to a charger. Here is a bidirectional charger that it can charge and discharge, sending the energy from the vehicle to the grid, or V2G. And this can act as a grid scale electric battery. This idea is becoming more and more feasible as the price of lithium-ion batteries continues to drop. So how much storage is in electric vehicles? Well, just as a quick back of the envelope calculation, we see that here, US to deploy 111 gigawatt hours by 2025. This is the number that we want. Just as a conservative estimate, we have 2.5 million EVs in the US registered today, around 40 kilowatt hours of storage per EV. That gives us 100 gigawatt hours of potential storage. That is very close to that 111 gigawatt hours. So, of course, we won't have access to that storage all the time. They're not always connected, and this is only short-term storage. But this highlights the big role that EVs will play in the future. That is, if we develop the correct structures and algorithms, which is what we're trying to do here in this project. So controlling one charging session is not enough. We need to aggregate and coordinate them at scale. The interest in VPPs has never been higher, and there have been many pilot projects. There have been some by Tesla, by GM, Ford, and Google. There was a project by Ford, Honda, and BMW that allows EV owners to communicate with utility companies. And very recently, and very importantly, Octopus is a utility company in the UK that offers a V2G tariff so that users can provide V2G at home. And this is out in the market right now. Our VPP takes into account all the new arrivals and departures. We put this with a V2G contract. V2G contract is an incentive that we design, and I'm going to talk more about that later. And then it makes a decision to charge or discharge at each hour of each operation day. And this energy is traded in the real-time electricity market. We can say this is an imbalance market, and the price changes at every hour of every day, and it's a single price market. So the first research question is, how do we design these V2G incentives? And well, to do this, we first need to talk about how a charging session is structured. We know that the EV arrives at some time with low energy, low state of charge, and it will depart with a higher stage of charge at a later time. We can charge at maximum power and then wait, or wait and then charge. And within that, we have many options, including ones with discharge. For our contracts, we are interested in two main numbers that describe the discharge. First is the discharge amount, and second is the discharge duration. The discharge duration is the latest point at which discharge can happen. After this is done, we are not allowed to do discharge anymore. So to incentivize the users, we borrow an idea from economics, which is contract theory. VPP, offers a set of V2G contracts to the agent, the AV owner, and the agent can accept a contract like this, or can also opt out. We present with them a menu of variable term contracts. These contracts are structured like this. Basically, we have 9 contracts, 3 columns and 3 rows, designed for 9 different types of users. These are organized in 2 dimensions. The columns are the duration, and the rows are how much energy we are allowed to discharge from the battery. And in the paper, we have all the optimization problems that we use to arrive at these numbers. The number in the middle there is how much incentive they're gonna get, how much discount in euros from their charging bill, basically. As you see, this increases as we go to the right and increases as we go down too. So once a person selects a contract like that, we can say that we have procured that flexibility from them. And second is, how do we manage charge once we have acquired that flexibility? So for this, we use a reinforcement learning agent. We also benchmark it against like MPC convex optimization approaches. So we use a soft actor critic, and the main feature is that its policy is a neural network. It outputs individual actions on how much to charge or discharge the batteries per time step. And then the environment handles all the arrivals, the contract acceptance, the charging, the battery simulation, the trading in the market. And then we output the state, an observation of the environment, and also the reward, which is the money spent in the market at each time step. Since we want to minimize this, we append that negative sign. And the way we design our agent is this. We focus on 2 main things. First, it needs to be scalable. If we want grid scale storage, we need our agent to work with an arbitrary amount of EVs. And second, it needs to be safe. By safety, we mean it needs to reach each EV's charging deadline. So we use the multi-layered approach here. In the bottom layer, we have all our EVs that are connected. Then they go into a flexibility abstraction layer, a virtual battery, through a process called aggregation. And then our reinforcement learning agent, which is that top layer there, receives the aggregate state and takes the scheduling decision subject to aggregate constraints. Then they take the aggregate action, and finally, the virtual battery will perform this aggregation to take the individual actions. So let's start with the aggregation part. So the first part is how do we construct the aggregate state? Well, we take the average of many of the features that are in the connected cars. We have the average remaining charge, the average remaining connected time, the average allowed SOC to discharge, and so on. And then we have one hard-encoded features of time, day of the week, hour of the day. We have the price predictions for the next 8 hours. And these can be perfect. And in our experiments, I'm going to show you what happens when we have a prediction error here. And lastly, we have the aggregate bounds. And these are all concatenated into a 1D vector. And what it's important here to note is that the dimensionality of this vector does not vary with respect of the number of connected cars. That is what we mean by scale. Then these aggregate bounds, let me show you how we construct them. So if you remember this figure that I showed you, we can have some constraints on exactly what types of trajectories we can take. And at each time step, we can say, okay, each card has a maximum and upper bound on the charge it can get and a lower bound. For example, if their EV2, its upper bound is 0, that is, it's already at 100%, so we cannot charge it anymore. Or we can have a V2G contract, so we can discharge, and so on for every single car. And then by simple aggregation, we sum the bounds, all the upper bounds together, we can get the aggregate bounds. And similarly with the lower bounds. And so this is basically the process that we take of going up the stack. Then our reinforcement learning agent outputs a number between 0 and 1. This is because it's activated with a sigmoid function, and then it's interpolated between the upper and lower aggregate bounds, and then it gets disaggregated. So the disaggregation, we wanted to be fair. By fairness, we mean we treat all vehicles as similarly as possible. And to treat vehicles, we need to define what do we mean by treating them. So we defined a utility function. This is a proportionally fair disaggregation, which we borrow from resource allocation. So we define a utility function that is all the energy that is allocated above the lower bound, which is this number here. And in the picture, I try to draw it like as similarly as possible for EVs. And what we find this by an optimization problem. We maximize the sum of the log utilities subject to constraints that the individual actions add up to the aggregate action, and that every individual action respects the individual upper and lower bounds. So the reason why this sum of log utilities works to provide us proportional fairness is that it's the same as maximizing the logarithm of the product of the utilities, which means like this function is maximized when all the numbers are the same or are as close as same as possible while respecting the constraints. So let me show you some experiments. How am I doing on time? Good. Okay. Thank you. Okay, so we studied the financial viability of this. So we have a data set with 10,000 charging sessions throughout the entire year of 2019 in the Netherlands. And then we have the hourly electricity prices in the real-time electricity market. And we also developed our in-house environment for charging sessions. This is available on GitHub and open source, and we try to do it as much as possible as like the RL gyms that are out there. So we compare our reinforcement learning approach with baselines. First, we have no control, which remember, it's like the charge at maximum power and then wait. There is no decisions to be made here. Then we have no V2G. This is an MPC approach that does not take into account discharge. So it's always like the SOC always increases monotonically. We have our linear program V2G, which is a convex optimization approach. And we have the optimal offline V2G, which they're both exactly the same, except that these two are vulnerable to price prediction errors. This last one will always have access to perfect price predictions. So let's see how we train. So our reinforcement learning agent is the aggregate soft actor critic, and we divide our data into training, which is January to June, and testing, July to December. So each one has 5,000 charging sessions, and then the length of each episode is around 4,000 hours. So we train it for 200 episodes. As we can see, it starts making random actions close to the no control baseline. These shaded area is the 5 runs, and the highlighted area is just one random run selected at random. And so it surpasses the no V2G baseline, and it continues quickly, and then it continues to learn until then it's close, but not too close to the optimum. And then for testing, we have this. So at testing, we run once, June to December. And this is that first part of the graph. On the y-axis, we have the cost, lower is better. And then as we go to the right, we increase the noise in the price prediction error. So as you can see, the performance degrades as we go to the right, the number increases. However, our aggregate SAC, the green one, degrades more slowly than the other two methods. This is because it was trained on perfect data, so it tries to recognizes the patterns, and the other two tried like the optimization approaches like overfit or are too brittle with respect to prediction errors. And so like here, in this case, like we can make a good case of why the reinforcement learning agent, or when rather, it would be like useful to use this if our forecasts are not that good. And lastly, another advantage of our reinforcement learning agent is just inference time. So Here is on the 6 months and our test data set to produce one feasible schedule. Our no control took a little bit less than a minute. That's the overhead of running the simulation. Then almost 3 minutes with our reinforcement learning. And the other two approaches, no V2G and linear program V2G, take 18 and 22 minutes respectively. So just some takeaways. Here, we designed incentives for private EV owners to provide V2G. We considered 2 dimensions of user types. We created feasible schedule for multiple EVs. That is, our reinforcement learning agent was safe. The disaggregation was performed fairly. The RL was able to transfer from train and then perform on a previously unseen data set test. The agent was robust to prediction noise, and a few future directions we can incorporate risk and uncertainty. Maybe there's like some hours of the day which is more risky to trade in. We can consider other flexibility resources. What happens if we have stationary batteries or productions, PV, wind, and also some grid constraints. We might have congestion signal as part of our reinforcement learning reward. So that's it. Thank you very much for your attention, and I'm here if you have any questions.